Welcome to everyone who is joining us today for this month's Quantum Marketplace on the potential of quantum networking. I'm Celia Merzbacher. I am Executive Director of the Quantum Economic Development Consortium, which is the host and organizer of this series. And we're delighted to see all of the returned attendees and new ones to learn about the potential of this industry, the state of it, from those who are really making it happen. So the Quantum Marketplace showcases QED-C members who are involved with various aspects of enabling and growing the quantum industry. It's a real pleasure to hear from the outstanding lineup that we have arranged for today. And as usual, I want to thank Mark Wippich and the team for all the work they do to put this program together. So without further ado, I will turn it back over to Mark Wippich and look forward to hearing all of today's fabulous presentations. So thank you.
Thank you, Celia. Okay, so quick background on logistics and format. Everyone is muted except the speakers. Feel free to send questions in the chat. And also a recording of this webinar will be posted in the future on YouTube. Okay, in terms of the agenda today, I'm going to give a quick snapshot update on the quantum marketplace itself, and then get into the potential of quantum networking, some overview and trends, and then getting into our today's lineup, and then a roundtable discussion, and then an upcoming webinar schedule. Okay, so the quantum marketplace, we've been getting tremendous feedback. It's been becoming very popular. For the presenters itself, it raises brand awareness, facilitates collaboration, deals, and partnerships. On the left here, the team led by Crystal has put together this directory on the QED-C member page, QED-C website, and you can click on the child page, which takes you to this directory of member companies that are listed and categorized by their input. And then these companies, the ones that would have the video icons next to them, they've given presentations in the quantum marketplace. So if you click on the company names, it leads to their profiles, and then you can reach out to them that way. And that's the web direct access address below that. And then also we have a YouTube channel. So, many people would like to have slides from these presentations or, background materials. We don't provide that, but you can go to the YouTube channel and see all the videos or webinar events that we have done. Okay, so in terms of some, potential quantum networking overview and trends. So, so a lot of us discuss, what are the use cases? What are the leading potential use cases? Because in this technology development, it's very, very early. So one of the areas is really, and we're going to discuss some of this today, is quantum safe security for real world digital platforms. What are the cryptography solutions in the future that resist or harden against future quantum computing capabilities and threats? And then another potential use case is distributed quantum computing. So that idea is to network quantum computers using qubits to enable solving harder computations and scaling to larger qubit machines. And then also as an area of distributed quantum entanglement, which is really teleportation over swapped entanglement, or another potential use case that's been contemplated is blind quantum computing. And then quantum networks for quantum sensing. There's various potential use cases in quantum sensing, but one of them that keeps coming up is relativistic geodesy, which is networking quantum atomic clocks to predict earthquakes and volcanic eruptions. Okay, so what are some of the platforms and subsystems of quantum networking, sort of different than classical networking? So there's post-quantum cryptography, which is PQC, which is encryption based on quantum computing resistant mathematics. And then there's quantum key distribution, QKD, which is encryption based on physics, not mathematics, and keys need to be passed. Then there's quantum entanglement, quantum memory, quantum repeaters, and there's also quantum transduction, a very early field, which is about how do we convert qubits through a state change, microwave to photon, photon back to microwave. and how do we go qubits from wavelength to qubits, wavelength 1, wavelength 2, and then also qubits going from matter qubits, or vice versa, from matter to light or light to matter. Okay, some more background or policy. Quantum.gov has issued a coordinated approach to quantum networking. If you haven't seen it, this is a great document put together by thought leaders in the space. Then also, which I think is also very important, is the NSA recently this month released an update to their timeline of all of this. I highly encourage people to see that as well. Okay, so let's get into the lineup. So today we have, Bill Tanzola from Accenture, we have Colin Suter from Deloitte, we have Michaela Mosca from EvolutionQ, we have Mahir from AWS and their new Center of Quantum Networking, and we have Steve from GE, and we have Jim from EPB. So with that, let's start off with you, Bill.
By way of introduction, my name is Bill Tanzola. I'm a principal director within Accenture's technology practice. I would say I spend the vast majority of my time helping our clients with their most challenging technology issues, which these days entail how do we make a rational business case to move our compute and networking and storage capabilities to the cloud. But I also serve in a secondary capacity. I serve as the communications and media liaison to our quantum computing organization. In this role, I help understand the implications of how quantum technologies are going to be affecting the day-to-day activities of our clients. As with many things, Accenture focuses on the demand side. So what are the business challenges that this technology can possibly help us? So we look at value realization, and when it comes to finding things, how do you industrialize delivery? A lot of this stuff now is based on activities that are done in the lab or done in Jupyter notebooks, but don't really address the modern IT requirements of our clients. And therefore, we specialize in helping bridge that gap between the two. Our program has been going on for about 6 years now, and it focused on quantum computing, as that was one of the first areas out of the gate with that approached capabilities that our clients could potentially take advantage of. We focus in 3 areas here: optimization, machine learning, and sampling and simulation. From my perspective, most of the work originally was in optimization, but then has switched over to machine learning as those capabilities have matured, both from a hardware perspective and a software perspective. More recently, we've looked at quantum networking. This technology is slowly coming out of the labs, off the tabletops, and are being deployed in test beds in order to try this out. This leads to the possibility of our clients asking us, why is this important to us? And we'll get into that shortly, but it is an area that we're looking at, and we focus again on 3 areas here: network simulation and emulation, because let's face it, a lot of the networks don't exist except for in theoretical models. Test beds, to the extent that the technology can be brought out and used to prove out business scenarios. We'll try that. And then I can't not discuss quantum key distribution. It is one of the first commercial technologies. It's following a different path in terms of how the networking aspects take place, but it is there nonetheless. And then finally, we look at this in terms of post-quantum cryptography. We refer this to as crypto agility. So as the industry matures, we definitely take the approach of zero trust security. So verify everything. Do not put all your eggs in one basket. And as a result, looking at quantum computing, quantum networking as a means of securing things should be done within a much larger context with overlapping layers of checks and balances. Now, we recently last year published a paper, and don't worry, I'm going to highlight this so you don't have to squint your eyes and look at it, on where the state of quantum networking is. I was one of the lead researchers on this, and we partnered with a company called Aliro Quantum on it. And it looked at really 3 areas where potentially we could add value, or companies could add value. needless to say, secure communications was one of the key areas. How can the various attack vectors be mitigated by using distributed entanglement in order to secure to send data, or not send data, teleport data from one area to the other. The second thing that Mark also mentioned is quantum sensing, which is the first use case that attempts to keep all data quantum, and then finally distributed quantum computing. Now, most of these are still very theoretical, which means that from where the people should think about how to do it is, one, learn as much as you can. I have a POV that, the link is on the previous slide. There are test beds out there, participate in the design and the development and watch their enhancements and exploits as they occur. And finally, look at QKD. If you're interested in that technology, then it's a good way of getting your feet wet and seeing if it is. Most people say, why should I worry about key distribution in general? Once you overcome that, you can then look at, is quantum computing or quantum key distribution a means of getting you to a more secure position compared to where you'd like to be? And then finally, embrace crypto agility. Attack vectors change every single day, and the prospects of quantum computing breaking things is a scary prospect. There are ways around it, and it should be looked at within a holistic manner.
So Deloitte has focused really into, you've probably seen my colleague Scott Buckles. He did a presentation previously on Marketplace and talked about some of the positive applications, let's say, of quantum computing in terms of simulation and modeling, logistical type challenges and so on. I am the managing director within Deloitte, and I'm the US quantum cyber readiness lead. So my perspective is really looking at, much as Bill had indicated, preparing ourselves for the time at which quantum computing computers, as they mature and they become technologically more stable. Kalamowska has done excellent work in that domain. I'm sure he'll talk about that later. If you look at the various timelines at play, one is, of course, the maturity of the computers themselves, Shor's algorithm, but you also have to look at, the possibility, as we understand, attackers today are stealing data on the premise that they will be able to break it tomorrow once those are available. Now, aggravating all of that as well is that actually implementing and updating to quantum resistant cryptography will take organizations years, if not decades in some cases, as we've heard it. So we prefer to think about it more as a risk management perspective rather than a specific date. I know that there's been a date around Y2Q that's been thrown out there. We prefer to look at it as really understanding what the risk can be, what your data are, where they are, what crypto's in place, and how long it's likely to take you to update that crypto, be it on enterprise or in distributed devices. And so that's the perspective that we tend to take there. So to get to that point, as I try to advance the slide here, having some challenges. There we go. To get to that point, we see the first instance really around quantum resistant cryptography, or PQC as it's been known historically. That is, of course, running on classical technology, mathematically based, very much deterministic. And I think that's a key point. I was actually reflecting back, 100 years ago, there was a lot of discussion around deterministic classical physics versus quantum physics, and PQC really is a deterministic process. Other processes that are quantum based, we think will take a little bit longer for people to understand. They're maturing. Later on, we do see positive application using artificial intelligence, machine learning, and we see a lot of optimism there, especially when distributed networks and sensors on the networks and so on are producing significant amounts of data that would need to be processed, by such devices. So what do we do about that then? Well, first of all, we have a suite of solutions. You'll get a link to that on the next page. But the other important thing that we've decided a few years ago was this field seems to be, there's a lot of conflation goes on in the field in terms of the applications of quantum, the security side, using quantum technologies. In fact, PQC, it's not a quantum technology, and yet it's got Q in the term. So we really try to get some clear, cogent messaging out there. And we partnered with the World Economic Forum over the last year. We've helped them stand up their quantum security initiative. The culmination of that was actually a report that came out last month. We provided our perspective on that pulling out the salient topics as we see them. That's the second link there. And then finally, a bit about our solutions and our offerings are presented there at the third link. With that, happy to entertain any questions in the Q&A and afterwards. Thank you very much, Mark and Crystal, for your organization and pulling all this together. Appreciate it.
Hello, everyone. Thanks for the opportunity to talk about how EvolutionQ is helping us harness the positive potential of quantum networking. I'm Michele Mosca, founder and CEO of EvolutionQ. I've been working in quantum computing for many years and in cryptography even longer. So EvolutionQ, how does it fit in the quantum space? Well, two different ways. For one, we're dedicated to helping the world securely and safely embrace all the positive potential of quantum computing. And secondly, we know that harnessing the potential of quantum networks to secure our systems will make our world more resilient and more secure. But we need to do that in practice. We need to do that scalably and so on, right? Practically and cost effectively. And so our products and services are dedicated, among other things, to doing that. Now, in the 1990s, if you talk to people about the potential of the cryptographic algorithms we're using to be broken systemically, it'd be hard to connect the dots to how that would impact our day-to-day lives. But today, there isn't a single aspect of our lives that isn't directly or indirectly impacted by cryptography. All of our critical infrastructures directly or indirectly depend on robust cryptography. So pretty much everything that is dear and important to us would be impacted by a systemic break of our cryptographic algorithms, whether by quantum computers or otherwise. So this is definitely something we need to get ahead of and get better at as we go forward and bet even more of our lives, right? Increase the stakes even further in the coming years. Our products and services, our solutions are about guiding organizations through the 4 stages of managing such a vulnerability. First and foremost, we have to acknowledge that there is a problem to be faced. And we've, for many years, been at the forefront of articulating the problem, doing careful analyses of the issues to help people understand and move forward. Now, the next step, once you acknowledge there's a problem, is to understand, well, but what does it mean to me? What does it mean to my organization? What do I need to do about it? And for that reason, several years ago, we pioneered the quantum risk assessment, which is all about understanding your quantum threat level, right? When you need to fix which system in what priority order. And then once you've done your quantum risk assessment, you have to do something about it. You have to mitigate the threat in some appropriate way. And we work with our customers to help them come up with appropriate roadmaps, ones that are timely, cost-effective, scalable, robust, to help them deal with this problem. Then, of course, you have to implement the plan. And an important part of the overall plan, an important ingredient of securing our most critical systems, is to deploy cryptography that is not just robust against the threats we know, but against emerging threats. And that's why QKD is such a valuable ingredient to add to our solution suite, but we need to do so in practice, efficiently, scalably, interoperably, and so on. And so we introduced the Quantum Delivery Network for doing exactly that. It's a simple, scalable way to design QKD into your platforms and even operate your QKD networks, get those keys, and deliver them to your applications quickly and securely. So if you're interested, if you share our view that we want simple, open, interoperable, and effective tools for quantum readiness, we can work together and advocate for that. If you, for example, provide QKD capabilities and want to translate them to end users all around the world in a scalable, robust way, we can discuss potential partnerships. And if you're an investor and you're wondering how quantum can create value for the world, we're happy to talk to you as well. We just completed our Series A, but we're happy to have a discussion about an eventual Series B. Thanks so much for your attention, and really looking forward to the discussion.
Hi, everyone. My name is Mihir Bhaskar. I'm a research scientist at the AWS Center for Quantum Networking. Before I dive into what we do there, I want to give a bird's eye view of quantum technologies at AWS. So at AWS, we're investing in the long-term potential of quantum technologies, and that comes in many forms. First, we created and launched Amazon Bracket. It's a fully managed service integrated with the AWS cloud that you can use today and gives access to a variety of quantum computers and really allows customers to play around and test hardware. Second, we launched the Amazon Quantum Solutions Lab, a professional services team of subject matter experts who can help AWS customers understand how they might leverage quantum technologies for their business. Third, and very importantly to our overall approach to quantum computing and quantum technologies, we launched the Center for Quantum Computing in 2019 in partnership with Caltech. And this is where we do research and development with the goal of delivering a fault-tolerant quantum computer. And finally, what I want to talk to you about today is the Center for Quantum Networking, which we launched this year. And this is where we, similar to the Center for Quantum Computing, do long-term research and development of technologies that we think could enable next-generation secure communications and cloud services. So first of all, you might be wondering why a company like AWS is interested in carrying out R&D to build quantum networks. First and foremost, it's because our customers are asking us, what should we do to prepare for a future where we have large-scale fault-tolerant computers, quantum computers? Well, we know very well, from as we've heard already, that quantum computers can pose a threat to certain encryption systems. And I want to mention that AWS is already very heavily involved in developing, validating, and deploying post-quantum cryptography. Even prior to NIST standardization, AWS Key Management Services has already incorporated post-quantum algorithms in a trial capacity that allows customers to begin preparing for these new encryption systems that will play a very important role in responding to potential threats of quantum computers. However, PQC is an approach that relies on computational assumptions, which could in principle be invalidated with any future advances in computing technologies. So to get fully information theoretic security, where we know the distributed keys will be secure forever, we need to use a physical key distribution technique. And this is where quantum key distribution comes in. If we can transmit quantum states between remote parties, then they can establish these future-proof, verifiably secure encryption keys. However, quantum key distribution is just the first technology available when we start thinking about being able to send quantum states over a network. And really the goal of the AWS Center for Quantum Networking is to explore the entire spectrum of capabilities of an advanced quantum network. In particular, a quantum network that's operating on a size, a scale, and a topology that's relevant for the AWS business and its customers. And so these kinds of networks, we can imagine, enable end-to-end entanglement delivery. And in such a network, not only do you get the advantages of information theoretic security of QKD, but you also have improved privacy. So the end users of the network, they share entangled states, and they don't need to trust any of the infrastructure providers or anything else that happens in the network. They can really trust the validity of that entangled state. So this enables improved privacy. We've also heard that distributing these entanglement between quantum modules is also a way of scaling up quantum computers, similarly to the way that our most powerful supercomputers are classical supercomputers are networks of CPUs. And finally, there's the potential for a fully blind quantum computing. If a customer has a high sensitivity compute workload, they would ordinarily need to maintain their own on-premises infrastructure. This might be especially challenging with quantum computing. So if quantum customers can access a quantum computer over a quantum network, they can submit their tasks to the cloud privately, enabling fully blind computing. So there's a number of potentially exciting applications, but this needs to be taken with a very large grain of salt. These applications are very, very nascent and very, very far away. So the goal of the AWS Center for Quantum Networking is to take a long-term perspective and lead the development of these technologies, both the hardware and the applications. So in that vein, one of our first initiatives is a very recently announced research alliance with the Harvard Quantum Initiative. So we're funding targeted research that we believe is really key to enabling quantum networks, providing resources for state-of-the-art fabrication for relevant devices, and probably most importantly, providing funding and scholarships at many levels, so undergraduate, graduate, postdoctoral, to help build the workforce of scientists and engineers that we believe will be bringing quantum technologies to commercial readiness over the coming decades. And so together with the AWS Center for Quantum Computing, now the Center for Quantum Networking, we really have a long-term vision for this nascent technology. And our goal is to assemble a leading team to solve these key R&D challenges and then make these technologies ready for the cloud and impactful for our customers. So with that, thank you for your attention. I have a couple of relevant links that you can take down, and I'll turn the conversation back over to Mark.
Okay, so I was asked to talk about the potential of quantum networking. I'm guess I've been slotted in the role of more the user perspective, which fits me and us here at GE pretty well, I think. And well, I guess I'll start out by giving a personal perspective, near-term quantum advantages and gaps that I see. And I may differ in some ways from a lot of the positive attitudes that preceded me. I take a little more skeptical view, and I have to survive here. And that is, for example, I'm in the benchmarking group looking at quantum computing benchmarking. And, you know, I don't get the sense that we're anywhere near having quantum computing ready yet or being a threat. But I do feel that quantum networking, and Mark and I had some arguments about, or debates, some nice debates about this, whether quantum networking is ahead of quantum computing in a sense. And depending on how you measure that, I think the standards community around quantum networking of necessity is further ahead than computing, because networking inherently involves getting devices to interconnect and talk to each other, and that can only be done through standards. And I do think there's probably nearer term opportunity in networking, like I said, than computing. And depending on how you define sensing, you know, I think, again, we can argue about where we are compared to sensing as well. But I do think quantum networking will be the glue for this quantum ecosystem that's coming up. Without quantum networking, nothing is going to talk to anything else, and it's you know, it's not going to be as good as it could be. So near-term quantum advantage, like everybody else, cybersecurity is the low-hanging fruit, probably the easiest thing to sell. You know, I would point to the NSA document on the critique of QKD, you know, specifically, and make sure that people are aware of the problems with QKD. And I was hoping to hear how they were specifically addressed in this webinar, but I didn't hear that yet. But cybersecurity, again, seems to be the low-lying fruit, and then sensor networking may be another near longer term than cybersecurity, but still near-term benefit. And again, quantum computing, yeah, interconnecting, you know, trying to get scalability for quantum computing is probably even further out still. So what are the gaps that I'm seeing? Standards for interoperable quantum computing networking components. Even though I said standards are further ahead, they still have a ways to go. Quantum photonic PIC chips and PDKs, process design kits, need to be developed so that we have tighter integration of things like QKD and other quantum networking components with the actual hardware in which they reside. Because again, if you have bulk optics and trying to connect that to as a QKD system to your equipment, there's a gap between the two. You know, I'd like to have my security physically integrated in my device, and that's only going to happen with, or most likely to happen with these PIC photonic integrated circuit chips. And another, for the longer term sensor networking vision, I think it'd be nice to get people thinking about quantum sensor output, not just quantum sensor detection elements, but output the data in a quantum state that could be processed from the sensors. But for all of this, for computing, which is being very harshly benchmarked right now, we also need network benchmarking, and we need better sensor benchmarking as well. So if you look at the, you know, I talked about standards being ahead for networking. This is our map that we've been developing in the QED-C of, you know, quantum computing, networking, and sensing. I know it's an eye chart and probably unintelligible, but I'll try to break it down a little bit. We have the subcomponents on the bottom. So the idea is you could take any standard that's being developed or that will be developed in the near future and throw it on this diagram. And then this diagram should be able to tell us, you know, what areas are being densely attacked through quantum network, through standards development. And then the white spaces in this diagram would tell us where standards are missing or being more sparsely developed. So anyway, sort of common subcomponents for everything on the bottom. We have our computing and sensing, standards development, and of course, applications on the top. And of course, we throw in PQC and these non-classical quantum inspired stuff. And by the way, this diagram is still under development. It's not the final version, but I just thought I would share it. But I think, again, networking is the glue that's going to connect all this together and make it work. Without the networking part, you just have two standalone pieces. Okay, quantum networking advantage. What would be the advantage? Again, I'm kind of reiterating cybersecurity, but that leads into some religious wars, PQC versus QKD. We look at it, I guess, as some people mentioned, as hedging our bets. You know, we want to have both and see where they best play out. Sensor networking, perhaps, but if you ask me, you know, where in sensor networking is there any possible advantage? Maybe in multi-parameter estimation over a network. And then the holy grail, of course, is scalable quantum networking, as mentioned earlier. I think everybody talks about that one. So a few more gap discussions here. Transduction needs to be addressed. Otherwise, the quantum network has nothing to talk to. The standards and benchmark. But the question is, how do you approach standards and benchmarks? I mean, everybody's very skittish about this. They say, well, we can't create standards and benchmarks until we reach perfection. I take the opposite view. Just create them now. Fail early. They're all going to fail. I mean, they're not going to be. The first standard of anything is generally not good. And so you need to start failing early, and you learn from that and build better and better standards. It's an iterative process. Again, I mentioned PIC chips and process design kits are needed for tighter integration. And it'd be nice to have quantum sensor output that remains in a quantum state. And I don't think quantum sensor folks think in this manner yet. They're all focusing on the quantum sensing element itself. So with that, I think that's all I want to say for now. So.
Okay, so I'm Jim Ingram. I am Vice President of Strategic Research at EPB in Chattanooga, Tennessee. I want to talk about a project we have underway here at EPB. The foundation of it is really our belief that energy and the internet will eventually converge together as a utility based on quantum technology. So who are we at EPB? We are a municipal utility. We have about 350,000 electric and broadband customers in East Tennessee and North Georgia, but the center of our service territory is really around Chattanooga, Tennessee. Pretty much every year since 2016, we have been rated #1 in customer service for electric distribution and internet by both J.D. Powers and Consumer Reports. Our brand really is Platinum Customer Service. In 2009, our company had actually no debt, and we did a $228 million revenue bond offer at that time to build a fiber optic network and smart grid in our service territory over 10 years. We deployed over 1,200 automated switches and AMI to every electric meter in our service territory. That took us from 11 million data points a year to 4 trillion. And we deployed a fiber to the home network that passes every home and business in our service territory. That investment in 2009 was forecast by an in-plan study I commissioned. It's used basically to say, what's the economic impact on a community if you build a sports stadium, an airport, a hospital, that kind of thing. Said over 10 years, we would see $600 million of benefit. 10 years later, I commissioned a study to look back at the actuals. It was close to 2.8 billion value to our community. This month, building on the EPB fiber optic success, we announced that we have deployed the Nokia 25 PON technology on network electronics onto our fiber system. It's a 3-year, $70 million capital investment, which will complete next year. But we now offer 25 gigabit symmetrical internet to anybody who wants it in our service territory. Our first customer was our convention center, and it will allow for a multi-port fiber connection through the optical network termination point to any customer. So if you want to work from home, go to school from home, game from home, you can have multiple fibers into your home to make those things come to life. We believe that the Nokia 25 PON network electronics will keep us on the cutting edge of internet service for the next 10 to 15 years. At the same time, we have invested $6 million in what we call the EPB Quantum Network. We have been doing entangled photon research on our fiber optic network with the Oak Ridge National Laboratory, the Department of Energy, and Cubatech out in San Diego, really since 2016. We started into the telephone business in 2000 by leveraging a downtown fiber loop that was part of the electric system. We're repeating that history. We're building a 7-mile fiber loop based on the OFS new low latency fiber that will pass through our building, through the Edney Innovation Center, which is a business accelerator in town, and across the campus of the University of Tennessee, Chattanooga. And it will include several of our substations, but it will give us a loop architecture, which will allow us to move these photons continuously around the track, 365 days a year, 24 hours a day, 7 days a week. We believe, and it is designed to be one of the first commercial quantum networks for researchers in our country. Why would we invest $6 million in building such a network today? Again, like I say, we've been working in this quantum space for some time now, getting some experience in that area. I mentioned that we believe that energy and the internet will converge, and quantum technology will be a key driver of the convergence. Electric distribution systems are distributing today. Transportation is electrifying. Electrification of transportation is the first new revenue stream in the utility business and the energy business since the advent of air conditioning. Those vehicles will become autonomous in time. The internet is already becoming a virtual environment. You call it a spatial internet, Web3, you can call it the metaverse, call it whatever you like. I don't know what it will turn out to be, but we believe it will be a fully immersive integration of the real world and a spatial world, where we will be living part of our lives, not in a two-dimensional way, the way we are communicating right now, but in a three-dimensional way. There will be decentralized finance in that world. Trade and commerce will change. Business will exist in it. Quantum networks will be key to making that world come to life, and we believe that it's going to be critical to managing the data, learning to manage the applications that will make the future utility services in our country more efficient, more capable of supporting economic development and quality of life. So why are we in quantum now? It's early. Regularly, as I attend these QED-C events, I hear regularly, these things are a long way off. There are a lot of reasons we're getting involved. We're not involved with this company, IonQ, but this is a story from the media. IonQ makes a quantum computer. There was a story in the trade press that was basically a hit job by an outfit called Scorpion Capital. They claimed that IonQ's technology, which is traded on the NASDAQ, didn't work. And then they shorted the stock. And basically, IonQ had to go to work to refute these rather shady characters at Scorpion Capital. We believe networks like ours that don't really exist today, as far as we know, will be a platform to prove new quantum technology's efficiency, to prove its performance improvement over time. That will show that the technology is investment grade. That is evidence of that. That will allow you to forecast time to revenue, and it will allow a mechanism to protect your brand. We believe this is one of the applications our network will be useful and valuable to. Because it is a commercially available network, it's available to the private sector, to university researchers, to federal agencies, to anybody who wants to do quantum research. Our employees, we want them to learn what this quantum world is. These are some of our engineers and technicians. And then on the right, these are some of our young people that we're actually training for the future to work in our company. When you say quantum today, quantum networks, quantum computing, quantum sensing, quantum worlds, people don't know what you're talking about yet. But we're getting our workforce ready. In January, when we told our engineers we're going to build this network, you know, they had a fit. If you know anything about engineers in the utility space, change comes hard for them. But 6 months later, they know what we're doing and they're on board. We want our employees and our community to know what we're doing. We also want our workforce to be ready for this quantum world, to build the equipment, to be technicians who will support the technology, including the engineers and scientists who will develop the next generations. We've been doing quantum key distribution research on our network. As I mentioned, we have a roadmap to a quantum protected network. I guess you can call it either one. This is Steve Morris, who's our cybersecurity director, but we will be using our network to move in the direction of protecting our critical infrastructure from any kind of intrusion. We believe the quantum technology will play a role in both our energy and our internet businesses. In the center here, you see one of our customer service reps in 2020. And again, we're as good as you get in the United States at that. This is what we think that customer service rep's job will look more like around 2035. On the right, you see a control center from Northrop Grumman. We think our control center will look more like this in the future. And we believe that the quantum technology will create applications that allow us to do things like learn how to charge electric vehicles faster. It's an AI, AR, VR, quantum age kind of service delivery environment that we want to be prepared for when it comes. I mentioned our Nokia 25PON network. We went from 11 to 21 supernodes or HUTs, distributed electronics on our system. We're pushing the electronics closer to the customer. When the time is right to invest and build a quantum network for our community, we want to know how to do those things. And we're starting today to learn how to do that. But we want to be prepared for that when the time comes. When we deployed our fiber to the home network, and we were one of the early communities to deploy symmetrical gigabit service, we were kind of branded Gig City. We hope when the time is right, our quantum network will lead us to be one of America's quantum cities. And this is how we hope to maintain both our community and utility leadership in the future. And that's my talk. I'll look forward to the Q&A.
So we can get into the panel discussion now. Okay, I'd like to ask Michaela first here. If we look at network security in a quantum-enabled world, your firm is primarily focused on enabling this in the future. What would you do differently?
Yeah, thanks for the question, Mark. Well, I would do this in the world. You can even drop quantum enabled, but I think the quantum enabled world has really made it clear we need to do this. I think we need to, the 90s were great, but we can no longer really live with the risk that our public key algorithms could be broken. So we do need more agile systems, as some people brought in, and we do need to go where the puck is going and integrate things like quantum cryptography into our platforms with an eye on getting what value we can today and scaling and continuing to reap the benefits of emerging technology as we go forward, instead of this fantasy that the stuff we have today is good enough, let's get it over with, and then have a big problem, because the legacy problems, the switching cost problems are just getting worse and worse. So let's just accept that things are going to change, unexpected is going to happen, and let's design that agility in and the readiness to embrace everything that the quantum world and other emerging tech is going to bring.
Great. And you made just want to note here, you made a distinction that the real area of potential threats in network security today is the public key security, not the symmetric key security, correct?
That's the known threat, and it's a bigger risk. I'm not saying we should be complacent about symmetric key either, but obviously it's the public key. But it's hard. I mean, most systems, directly or indirectly, would be affected by public key. But if you carefully engineer one that it doesn't require public key, then indeed you just have to worry about the symmetric key. But that's not easy to develop.
Yeah, right. Thank you. Here.
Yes, thanks, Mark. So I completely agree with everything that Michele said, and I think it's important. What I want to call out is that if we think about techniques like QKD or quantum networking, they're really only going to be one layer in quantum-enabled security stack. There's going to be many other layers, and we'll have to rely on and test and implement, these post-quantum cryptographic algorithms. There will need to still be very likely, the existing mesh of infrastructure upgraded, and so quantum key distribution and quantum networks really just provide that additional ability to generate the symmetric key and distribute it. And that's just one small component of a crypto system. So that's important for everyone to keep in mind.
Okay, great. Thank you. Bill.
I would agree. I mean, fundamentally, I don't think I would do anything differently, actually. And this whole notion of zero trust networks stays regardless of what technology, whether it's classical or quantum based. The fact that you should always have, from a security perspective, a healthy amount of skepticism around your technology, and whether or not you have thought about all the attack vectors that you could be subject to, they're always going to stand. I mean, just because you have switched over to quantum based solutions doesn't mean that the soft vectors don't exist. Social engineering will still be there. Your engineers will be still subject to the same type of scams that hackers use today to get access to networks. So fundamentally, I wouldn't change anything that I do today when thinking about network security, other than to make sure that I account for how quantum has changed for it. And does that mean I need to have an extra dimension of paranoia to address it?
Yeah, right. Colin.
So I think as many people have said, I mean, the quantum lens is a particular way that you can look at network security, but really the underlying conditions are largely the same. And I often joke that, it's never a bad time to go look in the attic. You don't know what you'll find. And oftentimes we come in on the understanding of doing a quantum assessment, and, you end up discovering things that the organization benefits from knowing, right? So I think it's a good trigger to take a look at it. The one thing, though, that another sort of trend I feel that we've talked about collectively is, when you're starting to look, and we see this with a lot of technologies as they evolve, right? They go through, potential standards, regulations, and so on. I think that one of the things that we are doing more now, and will continue to do more, is really just trying to clearly distinguish between different facets of technology, right? I mean, PQC, to some extent, it's a bit of a misnomer, really, right? Having the Q in there, I alluded to that earlier, because it's mathematically based, sort of classical cryptography. So that's one thing. And as I said in my briefing, to me, there's much more ability to have, for such a deterministic process, there's much more ability to have clear, concise standards that articulate what that is doing. As you move into quantum-enabled technologies, QQD and QRNG, understanding the benchmarks, as was talked about, understanding, the efficacy of them, exactly what they're doing, I think is going to be an increasingly important part. And I want to make sure that those two aspects are not conflated. So we will continue to clarify exactly what is happening with quantum-based technologies versus what is related to quantum, but not actually quantum, quantum derived or anything like that.
Yeah, thank you. Jim, you want to comment on this? Or are you good?
I think the only thing that I would say about this, if there was anything I could do differently or if I could change, it would be that I would accelerate our country's investment in solving these problems. We lead the world in patents in quantum computing, but we are trailing the Chinese in quantum network equipment. And these security measures, I can tell you from a guy at a utility, are expensive. And the risks are not, it's very, very difficult to get out ahead of the risks today. And since this war broke out in Ukraine, the number of attempts to break into our systems has only multiplied. And so if I could change anything, we would have started focusing our investment nationally in this area sooner than we have.
Yeah, I agree with you on that, Jim. Steve, I'm sure you have a perspective on this since you've been living it for quite a while.
Yeah, I guess I'll take two different points of view. One is, I guess the assumption that when everybody was talking was that they were using, I couldn't tell if they were using PQC or QKD in their solutions. And if they were using QKD, how were they solving authentication?
Yeah.
And I guess number two is, if it's a real-time control system, is PQC fast enough and providing enough security to handle, again, real-time controls in life-critical systems as we at GE have to do. We cannot afford to wait 2 minutes, for a security algorithm to operate. So it's got to be fast.
Yeah, and you're, without going into the use cases, but you're actively working with GE's product line to secure some of your product solutions, right? So you're literally living this every day, right?
Correct.
Yeah. Okay. So, Michaela, you're sort of I'm deeming you one of the resident experts here in this space. Any commentary on the prior answers?
Yeah, I mean, all great points, I think. I would want to follow up on something Mihir and Bill pointed out, which I totally agree with. There's many other threats out there, and they're not going to go away just because we have a wonderful solution to the key agreement problem. But I mean, all of these threats they're multidimensional, and it's a bit of an apples and oranges. Like, how do you compare a user error, which is one of the most prevalent threats out there, versus cryptography being broken? They're vastly different in terms of their impact, their likelihood, the timeline to remediation, right? And so they're all, I never would say, don't worry about patch management, don't worry about, user errors and all these other vulnerabilities. We absolutely have to worry about all of them in some sort of prioritized, balanced way. No one has the magic formula, but we try. The reason I'm particularly focused on cryptography, but again, I fully respect and support all the great work done and all the other vulnerabilities, is it's very systemic, right? So if you kind of organize them in terms of depth of impact, time to remediation, if it does happen, then obviously it's a very different profile than a buffer overflow, right? We kind of know how to fix that, right? But if the cryptography is broken, that's a whole other remediation plan. Again, all of these are serious threats. I am personally, focused on the systemic nature of the cryptanalytic threat.
Okay, great. Let me go to the next question. So this comes up a lot, and I don't want to spend too much time on it, but I do want to ask this question about, how useful is quantum number generation? This comes up a lot, so in terms of end users, right? Not the technology so much, but actually deploying this. what limitations of current technology, which is already very good and inexpensive, warrant investing in this displacement or potential displacement? I'd like to start with Bill.
Sure. So in terms of how useful quantum number generation is, I mean, I think back to the conversations I have with my own clients about quantum technologies more generally, and it's never focused on quantum advantage or quantum supremacy, but on competitive advantage. So the first question I would ask them if they came to me and say, hey, what do you think of quantum number generation is, I would ask them, well, what does number generation do for your business today? I mean, if you can't answer that question, then answering the question, is quantum number generation good for me, irrelevant for your business? So unfortunately, my clients do ask me about these things, and I generally ask them, how much of your business, how much of your revenue or your cost model is based on number generation, and none of them can answer that question. So I'm going to give a sort of a non-answer, because for my clients, it isn't a useful thing to them. I know it's out there, it's embedded in telephone, in various handsets, but at least at the level I deal with from an enterprise IT perspective, it really hasn't hit the radar yet as something they should be worried about. Now, my colleagues on this call could say, hey, Bill, just because they're not aware of it doesn't mean it's a threat or an advantage, but it hasn't seeped down to sort of at the enterprise IT level.
So you haven't heard a specific corner case use case where it becomes something very valuable? Okay, not yet, at least. All right. Yeah. So Colin, you want to add to that?
Yeah, thanks, Mark. So this was actually a topic, and I would say we recognized that there was a lot of vigorous debate around PQC, QKD, and QRNG as we were convening the workshops for the World Economic Forum. And we had a specific session on the advantages, disadvantages, and it was under Chatham House rules, so I won't give any attribution, but I can talk generally about some of the sentiments that were expressed there. Sure. First of all, I think, yes, there may have been some, I think it was maybe Steve that talked about religious wars. I mean, I think it was pluralistic, everybody came with their own opinion and had their own discussion. I think that at the end of that discussion, there was really a maybe not consensus, but at least a prevailing view. PQC, again, it's something that can be measured today. So probably the first out the gate there. QKD, as I think it was Steve that talked about authentication, that certainly was viewed as, there is a role for QKD to complement and work together. So it wasn't seen as one or the other. I think they were really seen together, particularly getting into some of the, the real-time control system type aspects that he also mentioned as well. QRNG, I think the notion there was, we don't know yet enough that the existing systems, the existing random number generation is not sufficient. However, the fact that it's verifiable random number generation using QRNG, they felt was somewhat of an advantage. So again, they were looking at these three technologies and trying to understand how they related together. And I think all three were seen to have a role, depending on the use case, depending on the architecture that was being used. So there was perceived to be an advantage, but it hadn't really been measured yet, which comes back to the benchmarks dialogue that we had earlier.
Yeah, thank you for that. Here.
Yeah, I won't say too much. I think Michaela is probably the expert here on this topic, but what I'll just say is that I see the value of QRNG from our perspective as they feed into the longer term protocols you would want to run with quantum technologies. When you're going the extra mile to secure networks with quantum technologies, then QRNGs will become an essential component, because the random number generation is essential prerequisite or ingredient for a lot of these techniques, such as quantum key distribution or more advanced protocols involving quantum networking.
Great, thank you. Jim?
Yeah, I think the only thing I'll say very quickly about this, we use random number generators today in all of our customer service activities, and all of our people are having to change their passwords every 5 business days right now. And so I mentioned that we have a roadmap to a quantum protected network, and that this is a part of that roadmap and part of the reason we're building our network, and this is one of the applications that we think will be an early adoption.
I see. Thank you. Steve?
I guess 2 points. One is There may be other uses for random numbers other than security. For example, network coding and compression. So, you know, I want to make sure we don't limit it to security. And I think, you know, the industry, again, does a poor job of benchmarking, and this is something that should be included in a benchmark. That's it.
Right. Yep. Okay. Michaela, last word on this one.
I mean, there's a lot that one could say. We actually did an analysis on it, which people are you know, might want to look at. Overall, I think it's something one should approach critically, but I do see value in some of the new features, like Colin pointed out, the ability to verify that there was, you know, fresh randomness created, and a lot of with fundamentally new features. It's normal for people to say, I don't really need that, or I don't know what I need that for. So we, you know, it'll probably take time for the true value or the greater value of QRNGs to be found. Of course, it's easy to find scenarios where I don't need it. You know, just don't be so sloppy with your classical RNGs because it's good enough. Sure, we know that, but let's focus on, you know, the non-trivial parts of that question. And there's certainly a lot more work to be done there. But I mean, randomness is, you know, cryptography is fundamental. Well, you can't have good cryptography without good randomness. So it's certainly something we tend to take for granted. Easy to screw up. There's lots, you know, validation is important. You know, robust failure modes is important. There's a lot of real world considerations here.
Right. Thank you for that. Okay, so I have two slides here, courtesy of EPB. Jim, I'm going to ask you just to talk for a few seconds on this slide and the next slide, then I'm going to get into the Q&A again.
Sure. So this is a very high level look at the EPB Quantum Network. There are basically 3 user lab sites and equipment sites on the network. One is here in our building. It's currently under construction. One is at the EDNI Innovation Center, which is a business accelerator here in town. QED-C, who is our partner in the network, has their offices, user lab, and equipment site in the EDNI building. And then at the University of Tennessee, Chattanooga campus is where the other one will be. That is part of the, you know, basically will be a 7-mile fiber loop that connects all of those. You can go on the next slide, Mark. This is a picture of the development. You can see our technicians working with the QED-C guys here. They're installing the LLS fiber I mentioned. On the left is the equipment rack, the first one that's gone in. This is QED-C's equipment. These are the photon generators, the controllers, and the detectors. There'll be 15 different user labs on the network. This is the control center, user lab, and equipment site in our building under construction. Planned to open July of next year, and we will be doing some focus groups actually this fall with institutions who may have an interest in using the network to learn from them what kind of services they'd like to see from it.
Great. Thank you, Jim. So, so what is the most valuable service one can provide with a distributed entanglement? This is sort of what we're contemplating here. And it's great to see EPB taking a step forward and you know, being a canary in a coal mine and building this stuff in the US. So what service can one provide that, you know, cannot be, you know, so really two points to the question here is, you know, first is what do you get with distributed entanglement network? And then what service can you provide that, you know, that cannot be achieved classically? And Jim, I'd like to come back to you just for a second on this. I'd like to go to Mahir since AWS is getting into this whole space. And I realize you're probably limited in what you can say, Mahir, but I think it'd be great to hear how you guys are looking at this.
Yeah, absolutely. So I think, yeah, focusing on what is one thing that can be done that cannot be achieved classically is or that quantum does better than what you would be able to achieve classically.
Yeah.
Is potential to actually perform private computations, have a fully private cloud. And so
blind quantum computing.
Blind quantum computing. So for example, customers that have high sensitivity workloads that they need to operate. They may be AWS customers, but they maintain their own on-premises infrastructure for critical computations, critical data. They don't move that off premises. And that could be because of regulatory reasons or because, of some sort of threat. In a network, an entanglement-based network where you can have these guarantees, based on, entanglement measurements such as measurement violation of Bell inequality, that information is securely transported across the network, you can actually access quantum computers remotely. And not only can you transmit data, but you can also program them remotely. So you don't have to ever reveal any of the inputs, any of the actual code, or the outputs of the algorithm. It's a completely encrypted computation. Now, it's possible to do this classically. It's called fully homomorphic encryption, but there's a massive computational overhead of many orders of magnitude for the best techniques we know right now. So it's not really done in practice. There are quantum techniques. It's a very nascent area. There's a lot, very, very long way to go before this is possible. But I think this is one thing that is really differentiating about quantum networks that's very interesting for us.
I see. Great. Thank you, Mihir. Jim, you want to add to that?
Well, I would say that there really aren't any limits that I could say to the kind of research that we would do our best to try to support on the EPB quantum network. I think the startup application that is happening on it today, because Qubitekk is our partner in the network, is they are deploying their next generation of quantum networking equipment on it. And so I think that, that's the first big application for the network, is testing new equipment.
Yep. Thank you. Just Steve.
Well, if I take your question literally, it's in the present tense. What's the most valuable service one can provide with distributed entanglement? Nah, I guess the answer is nothing right now. And I think that's, again, I hate to be a one-track person here, but benchmarks. When are we going to do something, some advantage? And we need to be carefully tracking that.
So it's actually, I would expand that comment, right? So you and I have talked about this. It's benchmarks, it's test beds, it's standards, as you're saying, and it's metrology, right? So we're early, but all these things need to be put in place before we can really get there, right? And that's why I think it's great that EPB is doing this, because they're building it, right? So which forces the issue exactly in benchmarking, which forces the issue on standards, which forces the issue on metrology, which forces the issue on all of it, in my opinion, right? Michaela.
Yeah, great question. I'm going to take the opposite interpretation or misinterpretation as Steve just has. And I'm going to just say this is kind of like asking in 1990, what's the most valuable service one can provide with the internet?
Yeah.
See, this is similar to what Steve, it didn't really exist in today's form back then. And if we tried to answer it, we'd come up with answers, but we'd really just be scratching the surface. But I'm not critical. I think we're not going to get there until we try, right? And bring the use cases to bear, continue to improve the technology. It's a process. And this is a great question, great answers, and we'll have even better answers, 1, 2, 5 years from now.
Right. Thank you for that. Bill.
I agree with everything that's been said. So I agree with Steve's statement. If you read it literally, nothing is the correct answer. I also agree with Jim's position. One step above that is build a test bed and test the equipment, hopefully get some answers that are useful to industry. And I agree with Michaela that we don't know where it's going to go. If I had to sort of shape my magic 8-ball, I would say that the most valuable service it can provide is secure communication for a particular type of threat. And that's what was mentioned earlier. Harvest now, decrypt later. And assuming that you have long assets that are in digital form, that are transmitted, that have long lives, then it's something that you should consider. I always, go back to probably one of the most boring topics in corporate policies, which is your document retention policy. Most companies get rid of all their data after 7 years, maybe 10 years, which means that those records that if their harvest is now are going to be destroyed before the technology is going to be around to decrypt them and make any sense of them. But if you do actually have assets that are longer than that, you should start looking at technologies that prevent threat actors from harvesting now and decrypting later. But I think that's going to fall to right now a very small set of people who have assets that have long lives of value that if in 20 years from now were revealed could cause either commercial, political, or social, costs to companies or society.
Yeah, Brian, thank you. Colin, last word on this.
All right, thanks, Mark. Well, firstly, I am firmly on the benchmark bandwagon. Let me say that to start. I definitely firmly behind that. I like Mahir when he's talking about all these, the remote access and sort of blind access. It was throwing up some memories around work that we did with NIST quite a few years ago on a privacy risk management framework, and that is unanticipated consequences. And I've seen some activities around this. I was thinking about, okay, blind access to quantum computer. What could that potentially do for geopolitical activities, right? In terms of being connected across different countries, there's huge consequences of that. I think that's the one thing that I think is often overlooked as these technologies come to market. Is during normal operation, there may be many unanticipated consequences. It is very important to be thinking about those as you're starting to develop the technology, rather than letting it lead you to where it wants to go.
Yep. And that sort of gets back to, not to put words in your mouth, Bill, but that sort of gets back to what Bill has said to me a few times and said it here as well, is, people should be investigating things to make sure they can find the competitive advantages. Right. So is and where are the competitive advantages? Right. Okay. So I want to go to the next question. So this is another one of these tough questions. I'm going to ask Steve first is, what does it take for a completely new communications technology to become standardized and commercially viable? I mean, you're an end user of this, you're supporting your, large clients, what does completely new technology and in terms of communications, what's this going to take in your experience?
It has to work. It has to do something useful. And again, I don't mean to be harsh, but if you look at like 5G is at least right now, is a huge success story, at least in terms of money. Time-sensitive networking was an example of something that started out here in the back room and is now almost the standard part of Ethernet. Ethernet itself is a huge success story. So the bottom line is it did something useful for somebody. And I think we often forget that simple fact. And we get too interested in cool technology. So again, that's why I come back to benchmarking. What is it doing better than can be done today? And that's got to be hit. That's got to be hit hard, very hard.
Yeah. Colin, in your experience, what does this take?
So I think it's interesting, even if you switch that sentence around, commercially viable and then standardization. And the reason I'm saying that is I think some folks were alluding to it earlier is, we look at as technology evolves, right, and it starts to have functional capabilities, as was just talked about, then getting the standards at the right level. I always feel like there's a right level of standards at the right time. I helped back after the tragic events of 9/11, we developed some of the biometric standards, sat on some of the ISO committees and so on. That at that point, the technologies had been proven and were commercially viable, but they were not sharing and they weren't setting up joint sort of guardrails in terms of future development. I think it is critical to get that at the right level, right? I've heard a lot from industry. We've talked about at some sessions in the past about, potentially there being too much standardization and that restricting innovation, which is a true statement. At the other side of it is the lack of benchmarks. And I think somewhere in the middle is often the case. And that's typically a great role that NIST plays, is setting up frameworks or guidance that are at that right level where it's outcome based and not overly prescriptive, that still allows innovation, but gives us some indication of relative performance so that people can make purchase decisions, integration decisions, and everything else that flows from that.
Yep, great, thank you. Bill?
I echo those same sentiments. I would reverse the order as well, with focusing on first on commercial viability. I mean, my clients are always interested in, will this make my life, is it cheaper, faster? Can I extend the life of an existing revenue line? Can I generate a new one? Can I generate higher margins? Those are the type of questions or lenses that the technology needs to be viewed within. And then I also believe in the invisible hand of the marketplace. I don't think, standardization should hold up progress. I think the market will sort itself out. At a certain point, will it make sense for standardization to take place? Yes. Look at the internet or intranets that are around. It required a certain amount of standardization for the technologies to talk to each other, but then vendors are able to go off and have their own extensions to the existing standards in order to add value that maybe the industry as a whole doesn't see or hasn't seen yet. So to me, flipping the order, focusing on viability, and then standardization will be a natural outcome of a competitive marketplace.
Yep. Thank you. Mihir.
Yeah, I agree with everything that's been said. So I'll just talk about a slightly different aspect of what it's going to take, which is really demonstrating the performance of the hardware that needs to be deployed, because we're talking not about new software or incremental upgrades to existing hardware, a completely new set of communication hardware. So really validating that, of course, in test beds, but then beyond test beds, also showing that there's a pathway to actually scaling this technology in a cost-effective way. So it's not a linear, price per qubit sent from the initial testbed implementations. And I think that's a highly non-trivial challenge, and there's a lot of R&D and engineering challenges of what are the protocols we're using, what are the materials we're using, and then what are the types of devices, and how can we access and robustly with high yield and produce these in a cost-effective way. And those are a lot of very, very challenging questions that will take a long time. And for the technology to be truly standardized and commercially viable on global scales, all of those questions need to be answered.
Yep. Thank you, Michaela.
Yeah, so I agree. I mean, great comments. Standards ultimately happen because users want them. There's commercial interest. So there's a little bit of a chicken and egg, because large scale commercialization won't happen without standards. But this is not new. It's sort of the Jeffrey Moore type cycle. You're going to have some early adopters and early believers who see the long-term potential, invest in it, move it along until it finally, crosses the chasm.
Yep. Great. Thank you. Jim, last word on this, since EPB is actually going to deploy something.
Follow the money. That's why we're doing what we're doing. Follow the money. The quantum computing, networking, sensing world is forecast to be about 85 billion by the end of the decade. If you look at the growth in venture capital investment in quantum technologies just over the last 3 years, it's been more than doubling. We believe that just like we went through a process, the 5G is a great example. There is a process of development, there's a process of testing, there's a process of adoption and deployment. And we are simply trying to position ourselves not to be the leader in it, just to be in the room and a part of it. And we think that that money solves problems. There are enough smart people in the world to solve just about any kind of problem, as long as the money has a staying power. We all know the federal government is getting ready to make some big investments in this space, and it's going to accelerate the process.
Great, thank you. Well, we have more questions. This has been an excellent discussion and great panel. I'm just going to go to the webinar. So we've had this list of topics already completed, and the potential for quantum networking, of course, is today. That'll be posted on YouTube probably within the next 3 or 4 weeks. Also, we have our next event lined up. We have the full cohort here. We have on November 3rd, we have QNEC, Alero, KI3, Qubitech, as Jim had mentioned, that they're working with NuCrypt and Verizon, presenting a user perspective. And this is going to be a little bit more digging into the actual solutions and products that would build out a quantum network. With that, I thank everyone.